Here we are, Unit 4, Lesson 10, I believe it is. We're going to take a look at compare all of the relationship models that we've looked at so far. So we've got 3 different ones basically that we have been using over the whole semester: linear, quadratic, and exponential. So you should have this handout and you should be filling it in as we're doing the lesson. So a linear relation has the equation y equals mx plus b. Generates a table of values, and if the first differences are all the same, that means in a table of values that it is a linear relationship. And first differences, you start at the bottom and you would subtract. So we'd subtract each successive y value. 13 take away 10. And you can see as we work our way up the table that our first differences are all the same, 3. When that happens, we know the relationship is linear. If I have a quadratic relation, that means that I have an exponent of 2 with x with an exponent of 2. If the second differences are all the same, the relationship would be quadratic. So the first differences you would subtract. That would be 9. 20 take away 13 is 7. 13 take away 8 is 5. 8 take away 5 is 3. 9 take away 4 is 1. And then the second difference is you take your first ones and subtract them. 2, 7 take away 5 is 2. 5 take away 3 is 2. And you can see that the second differences are the same. And when the second differences are the same, then it's a quadratic relation. So you can tell by looking at a table what kind of relation you have. And the last one, exponential. If there's a common ratio between the y values, the relationship is exponential. We just talked about this when we were writing equations. So a common ratio would mean that when you divide each successive y value, you would get the same answer because our exponential relationship multiplies by the same thing as the chart increases. So if I look at this one, I'd have 128 divided by 64, which is 2. And 64 divided by 32, which is also 2. And so on up my table. And so when I take and divide, and I get the same answer, that's called a common ratio, and that indicates that there is an exponential relationship. So when we compare the 3 types of relationships, we can compare their tables. Linear, the first differences are the same. Quadratic, second differences are the same. And exponential has a common ratio. If we compare the graphs of the 3 relationships, a linear graph we looked at is in the form y equals, the equation is in the form y equals mx plus b. So when we look at the equation, the slope is the m from the equation, which is the same as the first difference we calculated. In addition, the y-intercept is the b from the equation. So when I go to graph a linear relation, I would start at the y-intercept, and then I'd be able to use my slope to rise and run. So if I go back and look up here and look at my slope, my y-intercept was 4, and I should have a slope of 3. I rise 3 and run 1. Rise 3 and run 1. Rise 3 and run 1, which would make a nice line. What did I mess up? Oh, my scale. Oh my goodness gracious. Let's try that again. My scale is not 1. So I'm rising 3, 2, 3, and I'm running 1. There we go. Make sure you watch your scale. Don't make the same mistake I did. I'm rising 3 and running 1. Rising 3 and running 1. That's better. So you gotta be very careful with your scale when you do your slope. Rise 3, run 1. Make sure you're using your scale. A quadratic is easiest to graph when it's in vertex form, and then you can read the vertex right from the graph, or from the equation, sorry. So if I look back up to my equation, my vertex would be the P and the Q. Make sure that it's always the opposite sign for the P, for the X number of the vertex. And the A tells us the shape of the parabola by the step pattern. The shape affects how steep the quadratic is. So if I look at my table up there, 0, 4, the next point is 1 and 5. 5. The next point is 2 and 8. 2 and 8. And whoops, wrong way. The next point is 3 and 13. 3 and 13. And we get our nice curved parabola shape, our quadratic shape. The exponential graph the common ratio, or the R, affects the steepness of the curve. Which should make sense. The higher number you multiply, the steeper it should be because it goes up quicker. And then our initial value from our equation, the A, is the y-intercept. So if I go to make my graph, my y-intercept is 4, and I got a common ratio of 2. So I have 0, 4, I have 1 and 8, I've got 2 and 16, and you can see how steep my graph is getting. 3 and 32 won't fit on. And there's my exponential, my quadratic, and my linear one. So we looked at the tables, we looked at the graphs. Now we're going to look at some other information. So increasing and decreasing. A line is considered to be increasing if the slope is positive. So that means if the first differences are positive because it's the same as the slope. Increasing means it's going up to the right. Decreasing means it'd be going down to the right. So a line would be decreasing if the slope is negative or the first differences are negative. For a quadratic, the quadratic is increasing if A, the second differences are positive, and if the second difference decreasing if the second differences are negative. So same idea as a line. An exponential is increasing if the common ratio is bigger than 1, and decreasing if the common ratio is less than 1 but bigger than 0. So when we talk about growth or key information, the rate of growth of a line or the rate of decline, if it's going down, is constant. It stays the same over the same line. When you look at a quadratic, the rate of growth or decline increases over time because it curves. It curves up more steeply. And the rate of growth or decline as for an exponential increases as a percentage of the previous value. It's because you're multiplying each time by the same amount. It increases as a rate of the previous value. Okay, so those are the comparisons of those 3 types of functions. If you did not get any of it copied down, just pause and go back and get what you need.